So, welcome everybody to the Langtangen seminar. We're very happy to have you all back with us today. Today's speaker is our very own Aslak Tveito. I don't think he needs an introduction for Simulites, but for those of you who are not, Aslak has had a distinguished career in scientific computing as an applied mathematician. He received his PhD from the Department of Computer Science and Informatics from the University of Oslo in 1988, where he has also held a professorship for many years. Aslak has been with Simula from the beginning and also served as the CEO of Simula Research Laboratory from 2002 to 2022, a period that was marked by significant growth from 40 employees to our current 200 employees. And under his leadership, there were hundreds of master's students and 200 PhDs. Aslak's research is centered on numerical methods for PDEs and has evolved to focus on detailed mathematical methods and simulations of excitable cells in the heart and brain. His work has pushed the boundaries of computational cardiology, particularly in moving from millimeter scale models like the Bidomain model to micrometer scale models such as the EMI model, which probably will appear in today's talk today. I don't want to take up too much more time other than to remind you that if you have any questions, please pose them in the Q&A. And without further ado, Aslak, the floor is yours.
Thank you. Thank you very much. Thank you for this invitation. As you mentioned, I will talk about computational models of cardiac electrophysiology, and I will cover models on the millimeter scale, the micrometer scale, and something about the nanometer scale. But first, I would like to say a few words about Hans-Petter Langtangen that I worked together with for 30 years. He was a very, very dedicated researcher, dedicated teacher, a dedicated author, supervisor, and a superb colleague. He was what I would refer to as a computational philosopher, and he was always friendly to absolutely everyone, and he is deeply missed. Plan for my talk is first a little bit about motivation. What is it really that we are trying to understand? Then I will define some what I will refer to as standard problems in scientific computing. And the idea is to try to put up some problems that you will probably recognize in order to say something about the complexity of the models that we are dealing with. So it's a way to measure them, so to speak. Then I will say something about models on the millimeter scale. That will be mainly the Bidomain model, monodomain models, and they are suitable for simulating cardiac tissue, even whole organ systems. Then a little bit about models on the micrometer scale. That will be cell-based models, and that is suitable for smaller collections of cells, but not very small, so up to a few thousands. And then finally, about models on the nanometer scale, and that will be the Poisson-Nernst-Blanc model, and that will be used to simulate electrodiffusion near ion channels. And then finally, I will come with some predictions or hopes as requested by the organizers for the next 10 years. So first, what is it that we are trying to understand in this field? First of all, there are some very serious challenges to the scientific community concerning cardiac electrophysiology. 325,000 people die sudden cardiac deaths every year in US based on these illnesses, 250,000 in EU. The risk of getting atrial fibrillation that most of you probably have heard about after the age of 55 is actually 37%. That's exceptionally high. Some genetic mutations increase the probability of sudden cardiac death. And antiarrhythmic therapies and defibrillation remains to be optimized on an individual basis. Purpose of computations in the field of cardiac electrophysiology is, first of all, to understand this concept of electrical behavior of the heart, mechanisms behind arrhythmias. It's very, very important, very central. How arrhythmias can be prevented or treated with drugs is important. And again, impact of specific mutations has been studied carefully for at least 20 years. What defibrillation actually does and how it works and how it can be optimized. These are important questions. And cardiac electrophysiology based on mathematics or simulations, computational models, have increased quite a bit. Started in 1960 with a couple of papers by Dennis Noble. And then it has increased over the years. And nowadays it's about 250, 300 papers a year per year that is published in this field, and it seems to be increasing. One of the biggest, if not the biggest, challenge in doing this is dealing with several or many scales. So the clinical reality or the clinical situation is that symptoms and phenotypes appear at the organ and system levels, and drugs always act at the molecular scale. So the biological challenge is really to understand how molecular mechanisms shape, first of all, cell function, and how cell function shape tissue behavior. So biological systems span nearly 30 orders of magnitude in space-time. So understanding this coupling over these scales is very hard. And in terms of mathematical modeling, simulating multiple scales, spatial and temporal, in one computational model, that is perhaps the hardest challenge there is in computational biology. So then I would like to try to define some standard problems in scientific computing, and this is just to have something to measure complexity with. So I would like to start with what was a standard problem in 1985. I know this pretty well because I did my master's in scientific computing in 1985, and a standard problem at that time was to solve the Poisson equations, unit square, about 1,000 unknowns. That was a standard problem. We could also do variable coefficients, we could do nonlinearities, and we could do some not completely trivial geometries, but still Poisson equation, unit square, 1,000 unknowns is a reasonable description of a representative standard model. In 2000, a standard problem was perhaps still Poisson equation, unit cube, so 3D this time, and with 1 million unknowns. And we could do adaptive meshing, we could do sparse direct solvers, we could do preconditioned Krylov methods, a multigrid, and we could do somewhat more non-trivial geometries, but still the Poisson equation, unit cube, 1 million unknowns is anno 2000 standard type of problem. And what is the standard problem today? Well, I think that solving the heat equation, unit cube, 1 million nodes and 1,000 time steps. So you have to compute a billion unknowns. That is a standard problem today. It is still challenging, but within reach on most lab computers. And so today we can also do coupled system. We can do heterogeneous media. We can do adaptive time stepping. We can do solver parallelism. We can do realistic and complex 3D geometries, but still heat equation, unit cube, a billion unknowns to be determined. That is a standard problem today. But as you see from the picture here, we can do much more advanced things as well. So how do we estimate the number of unknowns to be determined in a standard problem? Well, we just compute the number of variables times the number of time steps times the number of spatial nodes and divide by the standard problem. Then we see how many standard problems do the complexity of this specific computation represent. And I will come back to this for the specific problems under consideration. So then for the millimeter scale. The millimeter scale in cardiac simulations is covered by the Bidomain and the monodomain models. They can be used to model cardiac tissue, and they are useful for doing whole organ simulations, and I will come back to exactly how useful they are. The Bidomain model looks like this. So it's a system of two partial differential equations coupled with a large system of ordinary differential equations. The main unknown here is V, which is the voltage and the transmembrane voltage. These are called conductivities. So it's a fairly standard model, but not completely standard model. So the monodomain model, and I will present that later, is somewhat simpler. That is a reaction diffusion equation coupled with system of ordinary differential equations. So I found a paper from 1984 where they were concerned about these Bidomain models with 1 million unknown, and they computed that it would take 3,000 years to solve that system. And then I have a comment that because of the uncertainty connected to 3,000 years, they will not start that computation, which probably fair thing. But it was regarded as a really big problem in 1984. Natalia Traunova, she is probably the most active researcher in this field. She has done lots of really important work, and she started early. And in 1993, she had a paper where she solved this equation with 257 nodes. But it turned out that 3,000 years was very pessimistic. So in 2006, a much bigger system was solved by Potze and co-authors. And in 2011, it was actually solved in 5 minutes by Niederer and his co-authors. And that was 1,000 milliseconds. It's done in less than 5 minutes using 16,000 cores. So a huge computer with 26 million nodes and 0.25 millimeter mesh resolution, which is the standard for the Bidomain model. So 3,000 was pessimistic. So what is the application of the Bidomain and monodomain models? It has been used extensively to understand and predicting cardiac arrhythmias. It can simulate sort of the mechanisms and give an explanation of what is going on. It has been used rather extensively to study the effect of different drugs and testing. So it's valuable in that respect. It has been used to simulate the effect of defibrillation, and even used to try to optimize the energy use of defibrillators and also pacemakers. And it has been used to understand different illnesses. This is a recent review of this field, and it's quite clear that this is approaching kind of clinical use. So Bidomain simulations today, I would say it is routinely used for whole heart electrophysiology in research. That is what is typically used for. It is accurate at the millimeter scale, typical mesh 0.25 millimeter, and it is approaching clinical applications. Some are pushing hard for that. It is still computationally demanding, but it's not impossible, and it's definitely not 3,000 years. So if we do this computation and try to estimate the number of what I refer to as standard problems, you typically have around 20 unknowns in the system because of the system of ordinary differential equations. You typically take, for instance, 1,000 time steps. A typical heart is 300 cubic centimeter, and then you have the mesh size, and then you divide by a billion, and you get 380 standard problems. So that's just in order to get a feeling for that. It's 380 times harder than what I refer to as a standard problem, but that's still doable. It's definitely doable on a national computer facility, but probably also in many labs. So to the challenges for the millimeter models, one thing that is actually quite interesting and strange is that in the Bidomain model there is no cell. So the extracellular space and the intracellular space and the cell membrane of all the cells, all of them are assumed to be everywhere, and the cell itself is not present. So it is, in some sense, a miracle that these models work, but they definitely work, and they work well, that they have given a lot of insight. But it is not without difficulties. So a typical Bidomain computational mesh is 0.25 millimeters, as I've mentioned. And in such a computational block, you can place between 100 and 1,000 cardiac cells. So that gives you a feeling about what the accuracy of the model really is. It is a coarse model. And then most of you think that, or no, not most of you, but some would argue that mesh refinement would be very useful. It is not very useful because these models have converged at 0.25 millimeters. So doing more mesh refinement is just a waste of energy. The cell will not reappear in any mysterious way. The cell is taken away in the mathematical model, so it's gone. So in the Bidomain monodomain models, there are no way to represent properties, sort of different properties, say, along a specific cell or specifically from cell to cell or things at that level. That is not possible to do in a reasonable manner. So Bidomain monodomain models are suitable for millimeter type considerations, but not for micrometers and definitely not for nanometer resolutions. Okay, so then we move on to the micrometer scale, and then we need models that definitely represent the cell. That's the essential thing there. And those models, there are several available, are typically useful for collection of cardiac cells. So that's where they come in. And one popular model at Simula, because this exact formulation has been used here, is referred to as the EMI model. And the EMI stands for the extracellular space, the cell membrane, and the intracellular space. That is sort of to highlight that all of these spaces are explicitly represented in the model. So this is a rough mesh of a cell. A cardiac cell is typically 100 micrometer long. The radius is perhaps 10 micrometer, and the volume ranges from 15 to 30 picoliters, depending on who you ask, really. The model is always used in 3D, or else there are some it doesn't really make sense in 2D, because then the extracellular space would not be connected. So it's always used in 3D, but it's useful to just look at the equation, what they mean in 2D. And this may look a bit, I hope it looks complex, but it's really just the Laplace equation in this extracellular space. Then it's the Laplace equation in the intracellular space. And then there are ordinary differential equations modeling what is going on across the cell membrane. And then there are continuity conditions across this membrane. So that is the EMI model, and this is for one cell. And then you can add cells, and you get some connection conditions on the gap junctions and so on. But this is the big picture. So how do you solve that? You solve this using operator splitting. So you typically solve the equation here, you solve the equation here, and you solve the equation across the membranes, and you glue that together in a reasonable manner. So here is the algorithm. You solve a system of ordinary differential equations first, and then you solve the intracellular potential here, and then you at the end of that time step, you solve the extracellular potential. So you will notice that all the steps in solving the EMI model they are really very classical. It is the Poisson equation, it is ordinary differential equations, and also if you look at the CPU efforts involved in this, it's really the elliptic equation as usual that you have to struggle with. And in particular, the extracellular space is rather large, and you have to use parallel solvers and things to do that if you are in a hurry. So what do EMI give you? It allows the modeling of, you can do non-uniform distribution of ion channels, and ion channels is really what governs what is going on the cell membrane. You can use it to introduce cell-to-cell variability of properties. You can have cell-to-cell variability of this coupling between the cells. You can represent what is referred to as the T-tubulars, so it's sort of invaginations in every cell. And you can have real geometries of the cells. That is possible in the EMI framework. And so that's all good, but EMI is extremely computational demanding. In some computations, we have seen that 2 micrometer is sort of the converged mesh resolution. And if you then consider 1,000 cells, you have 1,000 cells and 1,000 time steps. And you can argue that one cell is 16 picoliters, and then you have a little extracellular space. And you divide by this, and then you divide by the scaling factor of 1 billion, and you get that the EMI for 1,000 cells is 2.5 standard problems. And that's not too bad. That's doable. And we have done much more than that, and that's fine. But if we then go to the whole human heart, um, then you can consider 1,000 time steps. You can consider this volume of 300 cubic centimeters again, and this mesh size, and divide by 1 billion, and you get 37 million standard problems. So now this unit of standard problems, you see that you have 37 million of them, and that is out of reach. So I don't think anyone is able to use this model to simulate a whole human heart today. We have discussed if it's possible to simulate a mouse heart or things like that, but human heart is out of reach. But we can study things, so small parts of the heart. This is a simulation of the outlet of the pulmonary vein. The reason for simulating that is that you often see arrhythmias sort of starting in that part of the heart. And one difficulty is that the cells there are either part of the left atria or it is part of the pulmonary vein, and they have different properties. So that is illustrated here. And then if we have a normal case, we see that this wave goes one round and then it dies out. But if you have a certain mutation and you do the same simulation, you see that that wave just keeps on going, and that is the typical start of an arrhythmia. So this is a reentry, and it can typically start atrial fibrillation. So Bidomain models do not represent the cell, which is bad. EMI offers very high accuracy and flexibility, but it is computationally just too demanding. So we want to have something in between. We want to be able to represent every cell, but we don't really need to have resolution below the cell level. So that is why we started to work on what we have referred to as the Kirchhoff network model, and that is based on the Kirchhoff current law, which simply says that the sum of current into a node must equal the sum of currents out of the node. That is basic physics. It doesn't sort of add up somewhere. And the way we derive this model is just to use this for all the cells and for all the extracellular nodes associated with each cell. So we do this consideration by looking at one cell and all the neighbors and also the extracellular compartment. And then we do it the other way around by looking at the extracellular component and viewing all the neighbors. And we come up with two equations, and that is enough to compute all the transmembrane potentials. So if we now go back to the Bidomain model, it looks like this, and it's a very well-known trick that if you just assume that the conductivities involved here is related by a constant, lambda is a constant, then you will notice that you can add these two terms together, and then you can express this whole term in terms of of this, and then you can get rid of this term, and you end up with just one equation. So the monodomain model is then just a reaction diffusion equation coupled to a system of ordinary differential equations. So the reason for going back to the bidomain and monodomain model now is that we can do exactly the same thing with the Kirchhoff network model. Kirchhoff network model can be written like this, and then we can do the same observation. We can just do a very, very similar assumption, and we can write this Kirchhoff network model as kind of a discrete reaction diffusion equation. And it turns out that they result in solutions that are very similar, like the similarity between the bidomain model and the monodomain model. So what we need in the network models, we need the membrane capacitance. You need that in all these simulations. You need the area of each cell, the membrane area. You need the description of the membrane dynamics, and you always need that. And then you need an overview of all the cell connections and how well the cell are connected to each other, and how well the extracellular connections are. And if you have that, you can set up the model. Okay. So here I have a comparison of the bidomain model, the monodomain model, the Kirchhoff network model, the simplified Kirchhoff network model, and the EMI model. And the thing here is that we set up a problem that typically gives start of arrhythmia or reentry. And we see in this simulation that we start by 10 milliseconds, 30 milliseconds, 100 milliseconds, and 700 milliseconds. See that the EMI model and these networks model, they are very, very similar. But the bidomain and monodomain models, they don't pick up this reentry. So it sort of indicates that these cell-based models are more accurate. If you look at the computation time involved, the bidomain model took 55 minutes, monodomain took 25 minutes. The Kirchhoff network model took 36 seconds, and the simplified Kirchhoff network model took 7 seconds, and the EMI model took 5 days. And I think that illustrates the problem with the EMI model. And it also illustrates that these network models are very, very fast. So if we compare these things more qualitatively, I think I have to try to move this a little bit now. Which model is cell-based? Not the bidomain model, not the monodomain model, but these network models are, and EMI is definitely. If you look at subcellular resolution, so do you have resolution beyond the cell itself? That is only in the EMI model. If you look at how CPU demanding it is somewhat for the bidomain model, and not so much for the monodomain model. These networks model are fastest, but the EMI model is, of course, very CPU demanding. If you look at how easy they are to implement, bidomain model is deemed to not be so simple. That's a question of your, how experienced you are, perhaps. Monodomain model is easy to implement. These network models are reasonably, and this simplified model is easy to implement. The EMI model is not at all easy to implement. It's a hard one. Typical application, whole organ. this networks model, I say whole organ maybe because nobody has tried. That's yeah, not an old model. And for the EMI model, it's typically a small collection of cells that it's useful for. Okay, so then we come to the nanometer scale. At the nanometer scale, we use the Poisson-Nernst-Planck models. That is to study electrodiffusion. So that's a very accurate model that can be used to study electrodiffusion near the ion channels. The ion channels, however, there are 1 to 2 million of them in a cardiac cell, so it's a huge problem. But as a system of differential equations, it's just very, very nice. It is typical Poisson equation coupled to concentration equations that looks like this. So it's a diffusion term and then a little bit more. And this is formulated for the ions involved, which is typically sodium, potassium, calcium, and chloride. And this is a constant that is specified, and this is the electrical charge. So what is the complexity of the PNP? If you consider that the model has converged, if you have delta x equal to 1 nanometer, and that is reasonable, then you can compute the number of standard problems. So you have 5 variables. You have typically 1,000 time steps, 16 picoliter for 1 cell, and then 1 nanometer, and you divide by 1,000,000,000, and you get 80 million standard problems. So no one has used the PNP model to simulate 1 cell. That is out of reach. That is very, very, very demanding. But one application of interest is referred to as the cardiac diode. And if you look at this is a typical cardiomyocyte, cardiac cell, which is perhaps 100 micrometer long. So this is a collection of cells. This is 1 cell. And if you zoom in here, you will see that you have an extracellular space, you have T-tubulus, you have this sarcoplasmic reticulum, and you have this tiny, tiny diode, and that's where all the fun goes on. That's a very critical place in the cell. And if you look at that specifically, we can simulate what is going on here using this Poisson-Nernst-Planck model. So that is a simulation of that area. So the area in between here, that is the diode, and we have the extracellular space outside. This is the membrane. So yeah. So if we run the simulation now, we see that when we open the sodium channel, we have action going on both in the extracellular space here and in the intracellular space. And that will also affect all the other concentrations. And sometimes afterwards, we open the calcium current or the calcium channel, and we see that calcium flows into the cell. So that is the level where the PNP equations can be used and where they can be useful. So some conclusions now on the different scales, tissue simulations, millimeter resolution, whole heart simulations, EMI simulations, typically micrometer resolution. We can solve 1,000 cells, 50,000 cells, but not the whole human heart. And then the networks model, they have cell resolution. They are scalable to billions of cells, most likely. Ion channel simulations, then we need nanometer resolution, then we can get the debut layer, and we can typically handle tens of channels, but not the whole cell. That is not doable. So this, I have now summarized work that I've done together with all these clever people. They're all working at Simula, and then with some international collaborators, Calgary, San Diego, Berkeley, Linz, Bern. And I mentioned that now because now I will come to some predictions about the next 10 years, and I will not blame these people for for my predictions. So their responsibility stops now. And I will go to the predictions I have for the next 10 years. So the first prediction I have is that I think a standard problem in 2035 will be 10 to the power of 12, so 1,000 more than today. I think that in this period, there will be a lot of efforts concentrated around devising optimal solvers in the sense of Feynman, and I will come back to what that is. And I think there will be a transition from scientific computing to computational science, and I will explain what I mean by that. So, standard problems first. In 2035, I think we will easily be we have enabled solving problems with really complex geometries, and that will be easier to deal with than it is today. Also, realistic multiphysic model will be used, and I think there will still be limitations on space-time volume. That is a generic difficulty that I think will remain. I don't think we will be able to simulate a whole human being, for instance. Then I mentioned Feynman optimality, and I think I'm the only person in the world that is concerned about Feynman optimality, but I will explain what that is. You typically try to run a simulation in a small space-time volume, and you run that to convergence. So you figure out what kind of delta x, what kind of delta t do I really need to have convergence. And then you increase the space-time volume that you want to deal with. And then you require that the computational resources only increases in proportion to the volume. That is what you need from a practical point of view. You don't want an explosion in CPU efforts when you go from something that you know has converged to something much harder. And this is mentioned in a paper by Feynman from 1982 that I can recommend. And then finally, I think there will be a transition from scientific computing to computational science. And now I will provoke everyone that is working with scientific computing. So this is my view of scientific computing. You see here a person that is really well prepared to do something fantastic, and it stops there. And then my view on computational science is that the preparation is really exactly the same as in scientific computing. You really have to prepare very, very well, but then you also do the jump. And this is just a fantastic jump. It's the longest jump ever, 250 meters. So it is really, really nice. So in my view, scientific computing is preparations for real computations. It is about identifying a relevant mathematical model, typically in terms of differential equations. Then you have to develop efficient and stable numerical schemes. You have to represent geometry, boundary conditions, and so forth. You have to ensure that you have convergence, numerical correctness, and so on. You have to provide a working implementation, proof of concept, so to speak, and solve some examples. And then in computational science, you have to do all of the above. But in addition, you have to use the simulators to generate scientific insight. You have to compare with experiments and suggest new hypotheses. And you have to discuss relation to experiments. And I think that in 2035, the emphasis will be here, but it doesn't mean that you can cheat on this part, because then you don't really get good simulations. So you have to do both the scientific computing part and the computational science part. And if anyone is still here, thank you.
Thank you very much, Aslak, for the very interesting talk. I certainly learned a lot in the last 45 minutes. Marie, maybe you want to take the floor and ask the questions that were posed during the talk.
Absolutely. Thank you, Thomas, and thank you so very much, Aslak. I thought I'll start with two questions from the chat, more concrete ones. So the first one is regarding your example with the re-entry. And the question is, why don't the Bidomain or monodomain models pick up the re-entry in your example?
I don't know. So it is not like that the Bidomain model and the monodomain model cannot pick up re-entry. They definitely can pick up re-entry. In this particular case, they didn't pick up the re-entry, but we run both models to convergence. So we checked that it had converged, but it didn't pick it up there. But I have no specific explanation of that, but it's definitely so that it cannot pick it up. It definitely can.
Thank you. Another one here is in connection with the simplified network models. Is the cell model or the connectivity between the cells the most important in the cell models?
Yeah, it's very, very tempting to say both, but this is very different things. So the cell model determines whatever goes on over the membrane. And that's a very complex thing, and it's written probably 1,000 papers about that with many different models. That's a huge field. The gap junction or the coupling between the cells is most often, almost always, assumed to be much simpler. Most often a simple linear model, but there are more complex models as well. But so let me put it this way: the membrane model is clearly the most complicated one.
So thinking a bit further ahead about this, there's something that very tempting link to these graph neural network type models with the simplified kickoff network models. Do you have some thoughts on this?
No, I haven't really thought about it. I've just thought about it in terms of the Kirchhoff current law, and we derived it from there. Yeah.
Okay, so I have a few questions as well. So something I've thought about is, so if we think about the Bidomain regime versus the EMI regime versus these network regimes. So something that would be natural to say that an advantage of the EMI models is that you represent the shape and the geometry of each cell. which makes them suitable for investigating, say, structure-function relationships, how the cell shape, how the cell morphology affects the overall dynamics. And some would say that that's a key advantage of that representation. But then if you go down to the network model, then you lose essentially all the information about the morphology again. So then perhaps the advantage is more that you can look at these connectivity and more non-continuous features. Would you agree, or?
I would definitely agree. So I mean, the Kirchhoff network model and the simplified version of that, they are very simple models compared to the EMI model. The EMI model is very powerful. It's challenging, of course, but as you point out, you can really really dig into complex geometries, and that clearly has implications, perhaps especially for neurons. Cardiac cells are simpler, but you can do that, and you can also use it to consider contraction in a reasonable manner of cardiac cells. Yeah, so that's true. You get something by that complexity, but it's hard to use it for whole organ consideration.
So I have a final bigger picture question here. So at the beginning of your talk, you highlighted drugs and how they act at the molecular level to affect behavior at the tissue or organ level, right? And in at least in our experience from brain fluid research, you have the additional challenge that drugs are typically administered systemically, right? So they act at the molecular level and they reach everywhere. And this is a very harsh constraint kind of from practice on theory, right? Because it really puts a harsh constraint on the optimization problem of devising therapies or how to control the system. So I guess what I'm asking is that the computational model has a very large design space, but in practice, there's a very constrained design space. Do you see this changing? Do you see this as a barrier? Do you see this as yeah?
No, it just one problem related to this is that I mean one of the challenges in devising new drugs now is that they have unwanted side effects. So one big problem with new cancer drugs is that they have severe side effects on cardiac cells, especially the potassium currents, and they can produce prolonged action potential duration, which is not good. And it's really so bad that people in relatively large numbers start to die from side effects of the cancer drug rather from cancer. So that is a big problem. So research on cardiac drugs isn't really only about cardiac illness. It is about illness all over the body, where you try to use drugs to repair, as a cancer or neurological diseases and so on. But I see what you mean, that it is restricting what you can actually do. And I'm glad I do theory.
Thank you. With that, that was the questions on my list. So back to you, Thomas.
I think there was one more in the Q&A by Johannes. I don't know if you saw that.
I haven't, so if you could ask.
Yeah, it says, what is currently the largest feasible Kirchhoff model?
Mm, I don't know, but I think that you can apply the Kirchhoff network model whenever you have a finite element mesh, because you can use the nodes as the nodes in the network.
Okay.
That's my guess. So if anyone knows about the huge finite element mesh, that's the answer to Johannes.
Okay. Great. Then I would say I don't have any additional questions to ask. So I'd like to thank Aslak again and everybody for attending. And yeah, this will be on YouTube, as you know. So yeah, hope to see you then after the summer.